Hello, this is Kamran Swanson. Sorry I had to miss philosophy class today. To make up for it, I'm going to gift you a couple videos to help walk through the Venn diagrams, proving an argument using Venn diagrams, and then also something we just began talking about, but we didn't get into it, something called the Rules of Validity. So this video is going to cover three concepts. Uh, Proving arguments using Venn diagrams, uh, a concept called distribution, which is going to be needed for the next thing, which is proving an argument or categorical syllogisms with rules of validity. And below this video in the comments or in the video summary section, I will include timestamps. So you can go through the video or go directly to the parts that are going to be useful to you. Um, Something about this video, the good way to use it, the right way to use it, is to go through it slowly. You know, with the video, you have the option to stop and replay parts of the video that you didn't understand at exactly the pace that you need. So I'm going to try to go through things slowly and explain everything well, but I'm only going to do it once. Also, throughout this video, there's going to be a few exercises that I'm going to have you do. And the way I'll do this is I'll pose the question, and then I'm going to ask you to stop the video. And it's important that you do stop the video, try to figure out the answer for yourself, and then see how it's solved. That way you will know whether or not you actually understand it or not. If you just let the video play, we can fall into the trap of thinking we get it when we don't. And I think we all get that's not a good way to learn. So let's start off with the Venn diagrams. I'm still new to making these videos. It's been a while since I've made my last one, so excuse me for being a little clunky on this. So here's an argument, basic one that we'll start off with. All P are M, no S are M, therefore no S are P. So remember, in order to build a Venn diagram, or to see if you can test this out, what we're going to want to do, first of all, is to draw, our Venn diagram like so. So first we're going to draw one circle on the bottom left, like this. Another circle, and so we're going to call this our S. We're going to draw another circle to its right. That is our P, our major term. So S, remember, it's the predicate, the subject of our conclusion. That is our minor term. And the predicate of our conclusion is our major term, usually represented by S and M. And then our middle term is the M. That is going to be in both of our premises. The middle term is determined by being in both premises. So this is our M. Okay. Now we need to recall, and I'm not going to go over it again, but we need to recall how we used shading and drawing X's in Venn diagrams for our categorical statements. Now we're going to apply those same lessons to the categorical syllogisms with the three circles. So to start off, first we're going to do all P are M. So if you recall, all P are M is an A statement. No SRM is E. No SRP is E. All P are M is an A statement. It says all P are M. So when you remember what the A statements look like, if we were to say all S, and this is our S, all S are P, you remember that we shade in the S section that is outside the P. This means there's nothing there. So when I say all S are P, what we're saying is every single S belongs in the P circle, and that if it's outside the P circle, then it just doesn't exist. And that's what we're doing here. So you remember something like all chairs are furniture, or all dogs are animals. What we're saying here is that this area, which is chairs that are not furniture, these things don't exist. Chairs that are not furniture don't exist. Dogs that are not animals don't exist. And so we shade this area in. So bottom line, we have shaded in all S are M, we have shaded in the S, in other words, the subject circle. So for all P are M, now P is our subject, and we will shade in all the P that's both of these regions, all the P that is outside the M. Okay. Now, we see no S or M. To represent this, we remember that our E, I'll draw it down here, for E statements, no S or P, we shade in the center. That means that there's no such a thing as an overlap. The overlap does not exist, and so we shade it in. So no S or M, we shade in this middle ground. Now what has happened is that both of these premises have basically combined and given us a synthesis of these two pieces of information that we got from the premises. And the conclusion says no SRP. To see if this is valid, then, we want to look at the Venn diagram that the premises gave us themselves. And we ask, we don't put the conclusion here, we simply ask, is the conclusion already represented? Is the information that the conclusion is claiming, is it already there? And we see that it is, because no SRP would be the shading that is the overlap of S and P, and that's what this is. So up here, we got premise 2, these two shadings, and down here, these two shadings over here and over here, that's premise 1. So premise 1 plus premise 2 equals this, and that gives us a true conclusion. So this argument is valid. Now let's move on to the next one. Okay, so we're going to look at this argument. So this argument has particular premises. So if you recall, universal premises like all and no, those will use shading. And particular premises like some are and some are not, they're going to use X's. Now as a side note, that's going to change a little bit when we use Venn diagrams under the traditional methodology. In those cases, we're going to use X's for both particular and universal, but let's set that aside for now. Let's just learn the basics, and the modern version is the basic version. So in this case, just like before, we are going to use the 3 circles. We always do these 3 circles, and unless we make it very clear, and it's generally confusing, we should always make our minor term down here, our major term right there, and our middle term up there. And if you always do it in the same way, then it just reduces the confusing parts of all of this. Okay, so when we have a particular statement like some M are not P, and a universal statement like all S are M, we're always going to want to start with the universal statement. So even though it's premise 2, we're going to start with all S are M. So just as we talked about before, we are going to shade in the S, the part of S that is outside Rm. Okay. Then we are going to say, so some M are not P. Now this is where it gets a little confusing. So we have some M that are not P. So we know we want to put an X. And X represents at least 1. And it's what we use to represent some statements. It says some M, so there's at least 1 M that is not P. So we want to put the M somewhere over here. Now, as we discussed in class, we want to put it, this is what confuses a lot of people, so it's important to make sure we're straight on this. We're going to put that X right on the line, like this. What that represents is that we know that it's in this general region, but we don't know what side of the line it's on. Notice that the line that we don't know what side it's on is the S line. This is a little confusing because the statement doesn't say anything about S. And so a lot of people will put it on the line that is included in the statement. But because this S is not in the statement, it means we don't have any information about S. And that's why it goes on the S line, because we don't know whether or not that X belongs to S, been put right here, or doesn't belong to X and is put right there. So we put it on the line. Now sometimes we will be forced to move the X elsewhere, and that's fine, but for now we don't. Okay, so now we have the premises on the board. Let's check for validity. So I want you to pause this video in a moment here. I'll count down and see if you can figure out for yourself, is this valid or not? And then when you're ready, press play, and then we can walk through the answer. So on the count of 3, press stop. 1, 2, 3. All right. So hopefully you figured out the answer now. And the answer is that this is not valid. So why is it not valid? So the conclusion says some S are not P. In order for that to be valid, we would need to see one X, which we have, outside the P, because it's not P, which we have. This X is outside the P. So far so good. But remember that the statement is also saying some S. In other words, there's at least one S. In order for this conclusion to be valid, this X would have to be inside the S and outside the P. The X would have to be right there. But since it's up here, we're not sure. It could be this one, but it could be this one. And if our conclusion only possibly follows from the premises and not necessarily, then we're going to say that this is an invalid argument. This is not valid. So take a moment to look at this, and I'm going to pause, or you can pause the video, and we'll move on. All right, here we have 2 exercises for you to do. What I would like you to do, again on the count of 3, is take a few moments, draw Venn diagrams for both of these arguments, and determine if they are valid or not. Consider that these arguments look very similar, but there is one difference. That's going to mean a lot when it comes down to it. So on the count of 3, please pause this video and work these problems out for yourself. Then press play and we'll go over the answer. 1, 2, 3. All right, by now you should have worked out answers for yourself. We are going to go through them now and we'll see how it goes. So we are going to first draw Venn diagrams for this. We got our S, we got our P, we got our M. S, P, and M. We're going to do these simultaneously, so we're going to got our S, we got our M, that's bad circles right there, and our M. All right, S, P, and M. Okay. Now all P are M. Let's start up here, of course. All P are M, so we shade in the subject circle that's outside the predicate circle. We shade in all P are M. And then we're going to jump down. We're just going to do premise 1 here so we can see the difference. All M are P goes like this. Okay. Premise 2. We have no S are M. So with no S are M, we are going to shade in this part. Oops. And then with, I'm not even sure what I did there. Then with, I'm going to pause this for a second. All right, and then with the second argument, no SRM, we're going to shade that same area in that we just did. Notice that on the second one, we're overlapping. So it's like that second piece of information is kind of redundant. Only part of it's adding anything new. It should be a clue that there's something not enough with the second argument here. If you don't have as much information in the premises, you're not going to be able to conclude as much as the basic moral of the story. All right, conclusion, no SRP. So here, in order to establish no SRP, we need both of these shaded in, and indeed they are shaded in. Down here, no SRP, only one of those areas, only part of that's shaded in. So what that means is that up here, this first argument, this is valid. And your second argument down here, this is invalid because the conclusion is not in the premises there. And that's the official symbol for that. Okay, So let's move on to some particular categorical syllogisms. All right, here we have two arguments that include particular statements, quite a few of them, in fact. So at the count of three, I would like you to draw your Venn diagrams and see if you can figure out if these are valid or not. Please pause this video on the count of three. 1, 2, 3. All right, welcome back. By now you should have figured out whether or not these two were valid or invalid using Venn diagrams. So let's figure this out. So we're going to start with the top one. We're going to do these ones one at a time because they're quite different. All right, so we got our S, we got our P. I'm not even going to write the letters now. We're good to go there. So some P are not M. So if this is our P circle and this is our M circle, there's at least one P. Some P are not M. We place the premise 1x right there. Second, some S are M. So now we know that we have one S that is an M, but we don't know if it's a P or not. So we place that right there. Now, before we get to the conclusion, just consider these X's can be on either side of the line. So maybe both of them are outside the center entirely. Maybe they're both in the center. Maybe one's out, one's in. There's no way to know. We just don't have enough information. The conclusion, some S are not P, would require that we have one X firmly in the S outside of the P. Now, this X might be that S, but we can't know for sure. And since we can't know if this X is the X of our conclusion, then this argument is invalid. Next, and then we're going to move on to a different topic entirely. Okay, so again, if you have a particular statement and a universal statement, you're going to want to start by illustrating the universal statement because it helps us keep things straight. So all M are S, we are going to shade in this area. Second, some M are not P. So now we're going to draw an X inside the M outside the P. Now you remember from before, if we don't know what side of the line it's on, you put it on the line. But since we know nothing is here, it forces our X to be right there. Our conclusion says some S are not P. We need an S. We need an X in the S region outside the P region. And that's what this is. Notice how it's inside the S circle, but outside the P circle. Therefore, our conclusion in this case is valid. Okay, so Cyclops. Cyclops is happy. All right, let's move on to a new concept. We're going to call this, this next concept, distribution. So distribution is a weirder concept within all of this, and it's being used for the sake of being able to use the rules that we're going to get into momentarily here. I highly recommend going through the book carefully on this and really getting a solid understanding of this. Although you can usually get by if you just memorize some things, but I think as we've learned by now, to understand something is always going to be far more valuable in this class and for this material than simply memorizing a chart. So one thing to know about this distribution is that, we've had a few concepts. We've had validity and invalidity. We've had true and false. Validity, remember, applies to arguments. Invalidity applies to arguments when we have multiple premises leading to a conclusion. We have true and false, which does not apply to arguments. It applies to individual statements, to propositions. So every proposition is true or false, but arguments are not true or false. They're valid and invalid. Distribution applies neither to arguments nor to statements. Distribution applies to individual terms. So notice that we have what is basically, we could say we have two terms on this table, S and P, but in another way we have 8 terms. We have this S and this P, this S and that P, this S and that P, this S and that P. They're all occupying basically a different position in different statements. This is the subject of the A, this is the subject of an E. And so in that sense, they're different. So of each of these terms, we're going to say that each one is either distributed or indistributed. And the pattern that this creates is going to be an important one for us. Okay, so we're going to start off by saying this, that a term is distributed if the statement is making a claim about every member of that class or every member of that term. So go over that again if you need to and read it in the book, of course. But as an example, the A statement is always the easiest thing to understand. When we say something like all dogs are animals, we are saying something about every single dog. In other words, we're saying every single dog is an animal. Because we are saying something about every single dog, we're going to say that the subject is distributed. What's important for this is that this is dependent not on dogs, it's dependent upon its place in the statement. That means this, and this is very important. Every A statement's subject term is distributed. The subject term of every A statement is itself distributed. There is never an exception to that, period. And all of these are going to work that way. Once we figure out if the term is distributed, and I'm going to put a D for when they're distributed, and a U for when they're undistributed, that's always going to be the same, and that's an important thing to keep in mind. Now, we said that we're saying something of every dog, but we're not saying something of every animal. We're not saying that every animal is a dog, of course. That's not what all dogs are animals means. So the predicate animals is undistributed, and that's just a feature of all A statements. The predicate is undistributed. We're going to go through a few of these a little bit more quickly. Of course, you can always go through it again. No S or P, so imagine no dogs or cats. In this case, we're saying that every single dog is not a cat. Since every single dog has the property of not being a cat, we're going to say this is distributed. Likewise, every single cat has the property of not being a dog. Therefore, the predicate is distributed. E statements have both distributed terms. Some S or P, some dogs are good boys. Here, we're not saying something about every dog. We're only saying something about some dogs. Therefore, this is undistributed. The subject of an I statement is undistributed. Meanwhile, we see that not all good boys are necessarily dogs. I mean, a hedgehog can be a good boy too. Lots of things can be a good boy. Therefore, since we're not saying something about all good boys, we're going to say that this is undistributed. Okay. Some dogs are not friendly. We're not saying something about every dog. Therefore, this is again, I'm sorry, it's not distributed. This is undistributed. We're not saying something about every, hold on a second. Bam, there we go. This is undistributed. All right, now here we're the last one. This is the most strange. It's the strangest one. It honestly took me a little while to wrap my own head around this the first time I learned it, but I think we'll get it. I'm going to cut to the chase here and then explain it. This is distributed. It seems like it might not be. I mean, after all, if some dogs are friendly, means that dogs is undistributed and friendly is undistributed, then some dogs are not friendly should do the same thing. Because after all, we're not saying that all friendly dogs are friendly. We're not saying that all friendly dogs are not friendly. It seems like it should be undistributed. And this has been a kind of a debate, at least it used to be, in logic, whether this should be distributed or not. But like, why would you even distribute it in the first place? And the answer basically goes something like this. Some dogs are not friendly. When we say that, we're saying there's at least one dog. So we're talking about one dog is not friendly. We're not talking about a portion. In a way, we're not talking about a portion of dogs and a portion of the friendlies. We're talking about one particular dog. Let's call him Fido. Fido is not friendly. You know what we know about these friendly dogs? None of them are Fido. Not a single one of these friendly dogs is Fido. In fact, all of the friendly dogs have the property of not being Fido. Look, it doesn't matter what we're saying about all the members of the class. All that is important is that we are in fact saying something about every member of that class. Therefore, this is going to be so hard to remember for some of us. The predicate of the O statement is distributed. You think about why that's different to up here. Some dogs are friendly, so we might say, what if we're talking about Fido up here? We're saying that Fido is a friendly dog. But we're not saying of friendly dogs that they're all Fido, and we're not saying of friendly dogs that they're all not Fido. So we're not really saying anything about all the predicates of an I statement. So I'm going to clean this up for you. And this is the pattern that will always be, and it's worth remembering, but this is always going to be how it is. The A statement, it goes distributed, undistributed. E, distributed, distributed. I, un, O, undistributed, distributed. You can notice a few patterns here that will help you remember this. Notice that our two statements that have been symmetrical for everything else continue to be symmetrical here. That these two, the E and the I, those are the two statements that you can do conversion on, simply switching the subject and the predicate. They're also the two statements that their Venn diagrams are symmetrical, that when you flip them around, they look exactly the same. That's not true of the A statement, and it's not true of the O statement, which in all other cases have been asymmetrical, and they continue to be asymmetrical. The universal statement of the E is distributed in both cases. In a sense, it's a more powerful, much stronger statement than its contradiction, which is the opposite distribution for both terms. And so as they were opposite in the square of opposition, so the I and the E are opposite here. Likewise, you notice the A and the O, contradictions in the square, are likewise opposites here. Where the A is distributed, the O is undistributed. Where the A is undistributed, the O is distributed. And they're the reverse images of each other. So I just think it's interesting and also helpful to remember these patterns because it just helps the whole picture fall into place. All right, keep these in mind. If you haven't already, write these down in your notebook. Keep these to the side because I'm about to erase this. And this information is going to be useful for the next stage. All right, this next thing that we're going to go over is called the Rules of Validity. These are 4 rules for the traditional square and 5 rules for the modern square. It's the same first 4 rules, and then the modern square has an additional rule. We can apply these rules to any of the 256 categorical syllogisms. And when you get good at this, you'll be able to figure out within just a few seconds, without drawing or anything like that, whether or not the argument is valid or not. Once you get used to these rules, they're very simple to apply. Some people still prefer the Venn diagrams, and I think the Venn diagrams are interesting. They show you things that the rules don't. But ultimately, when I'm looking at an argument, I always use the rules because eventually they're just much easier to use. So there are 4 of these, and let's introduce them one at a time. The first rule is the middle term must be distributed at least once. So you remember the middle term is found in both of the premises. It can be either in the subject or the predicate slot of each of these premises. Depending on which statements you have and where the middle term is going to be distributed in some cases and it won't be distributed in others. So to think about this, consider an argument with 2 E premises. You remember from our previous lesson that in E statements, both the subject and the predicate are distributed. Therefore, it's always going to be the case. If you have at least one E premise, the middle term will always be distributed at least once. If it's not distributed, so you think about, suppose you have two A statements, and the predicate is not distributed in either one. If you have a figure 2, it's going to look like this. And so this is figure 2, and since both of these are going to be in the undistributed predicate slot, this will not be valid. However, if one of these was switched, if this was all MRP or all MRS, then the term would have been distributed at least once. It's okay if it's distributed more than once, but it has to be distributed at least once. You can I'm not going to go through every situation, of course, but you can think about all the possibilities. So long as you have one E statement, it's always going to pass Rule 1. If you have two I premises, it's always going to fail Rule 1, since I's don't distribute anything. And we can just already imagine whole groups of arguments. So we know that all AA whatever 2 arguments are going to be invalid just from this. We know that every argument that starts with an II is always going to be invalid because it can never pass Rule 1. All right, let's move on. This might be the rule that people confuse the most. If a term is distributed in the conclusion, then it must be distributed in the premises. So in other words, if you have an argument like this, we see that this breaks Rule 2, because here we have our S in the conclusion, distributed. The subject of the A statement's distributed. If a term is distributed in the conclusion, then it must be distributed in the premises. But it's not distributed in the premises. Therefore, this breaks Rule 1. And when it's the minor term that breaks the rule, we call this the fallacy of the illicit minor. The predicate here, the major term, is not distributed in the premises, and it is distributed in the premises. I'm sorry, it's not distributed in the conclusion. It is distributed in the premises. There we go. That's okay. If you have a term that's distributed in the premises but not in the conclusion, that's not a problem. All that matters is that if it's distributed in the conclusion, then it must be distributed in the premises, but it doesn't go the other way around. Keep in mind that with Rule 2, an argument can actually fail this rule twice. Can you think about what kind of argument would fail Rule 2 twice? I'm going to pause the video and I'd like you to think about it and then move on when you're ready. 3, 2, 1, pause. If you have an argument that ends with an E statement, the conclusion is an E. A conclusion with an E statement means that both terms are distributed. But in this case, we see that it's distributed here, not there. It's distributed here, but not there. That means that this rule fails both the minor on the minor term and the major term. So it commits the fallacy both of the illicit minor and the fallacy of the illicit major. All right, let's move on to the rules 3 and 4, which deal with negative premises and conclusions. Rule 3 is there can never be more than one negative premise. Basically, if you have an argument that is of the mood EEA or EOI, it's always going to fail. If you have an argument with two negative premises, E's and O's, then it's always going to fail. You can have two affirmative premises. You can have 0 negative premises, but you can only ever have at most one negative premise. The fourth rule: if a premise is negative, the conclusion must be negative. If the conclusion is negative, one premise must be negative. When you think about it combined with Rule 3, that means you will always have either 0 negative statements or 2 negative statements. And when you have 2, they will bridge the premise-conclusion line. In other words, if you have, oops, that's really sloppy here. Let's erase that. If you have premise 1 being negative, premise 1, let's say this is an E. Premise 2, let's say this is an A. In our conclusion, let's say this is an E. We have two negative statements here, and they bridge the premise conclusion line. You will never see both negatives on the same side because then it would violate Rule 3, and they wouldn't fit down here. We can have all affirmatives. We can never have two affirmative premises and a negative conclusion. Those will never result in being valid. So these are the 4 rules, and that's all of them. We'll deal with the 5th rule on another day. But if you can apply these rules to any of our categorical syllogisms, you will be able to find the same answers that you could using the Venn diagrams. For some people, this means you can do it more reliably. I should note that so far we have learned Venn diagrams under the modern, because Venn diagrams, the modern version, has less components to it, and it's kind of easier to learn. On the other hand, with the rules, we have learned the traditional. So this is the only time where you're going to find differences, is when you see, so this is the basic rule. This is everything about how these end up being different. You know what? I'm just going to give you Rule 5 right now. Rule 5 says that if there is a particular conclusion, an I or O, then at least one premise must be particular too. When you think about it, a particular conclusion, when you think about the Venn diagrams, a particular conclusion is always claiming an X. In order for this conclusion to follow from the premises, one of these premises needs to give us an X as well. That's what this rule, rule number 5, is requiring of us. If both premise 1 and 2 are universals and our conclusion is particular, then our conclusion requires us to establish something that the premises don't give us. And that's bad. That's invalid. So these are all the rules, and you can apply them for any of the categorical syllogisms. I would encourage you, as you're practicing, as you're learning this, try out both of these methods, and you should always, always, always get the same results, Venn or the rules, with the one exception that if you're dealing with an argument with two universal premises and a particular conclusion, then your Venn diagrams are going to give you one answer, and your rules without this are going to give you a different answer. So that's all for this lesson. It's 40 minutes that we got here. If you have any questions, make sure you bring them to class on Tuesday, and I will